Hello, good morning, and welcome back to Refactoring Bitcoin. After my previous video, I have received the question, are you planning to use concepts in your API? And when you look at the Bitcoin kernel API, you see that for the most part, it provides concrete types like the block and transaction and inputs and outputs. And of course, it will also have classes to manage the chain, and it has functions to validate blocks. Um, but there are no really use cases for generic types or like containers or algorithms. Of course, they will be needed internally, but not at the interface level, not in the API. So, but I had some ideas how I would like to introduce concepts in a video, but I just did not know where this would fit in the Bitcoin kernel API. So when would be the right time to give an introduction into concepts? And also, since concepts is quite an advanced topic, and my goal for this channel is I want this to be beginner friendly. Um, and you might ask, okay, if this is supposed to be beginner friendly, then why did you start with topics like type erasure in the first place? And I want to explain that. When you start with a new programming language, you do not really start with the basics, right? Um, you start with the motivation, and then you dig your way through to the basics. And yet, most teaching material actually starts with very basic stuff like if conditions and then for loops and how the stack works, etc. This is overwhelming for beginners to go into the syntax so detailed. So therefore, I structure this course, this channel also with a motivation. We start with a high level part. I introduce things like type erasure, and then over time I will explain why this is needed and why this is helpful and what the coding style is supposed to be and coding guidelines and tricks and design principles, etc. Okay, but back to the question that I received. I just want to read my response. I wrote, I will definitely cover concepts in a video at some point, but I don't see a use case in the kernel API. And I continued and asked back, you probably ask because of the interface types in the current API. I have ideas about them that do not involve concepts. You remember when I say interface types, I'm referring to things like the validation interface, where I said that this is not really C++ terminology. This is when you have an abstract base class and you call that an interface, this is Java terminology, not C++ terminology. And the question that I got back, or the answer that I got back was, I have asked because concepts naturally fit in the type erasure design pattern. And of course, that makes total sense. I did not think about this, but this is the perfect bridge. This is exactly how I can lead to the thing that I want to show next. So thank you very much for this advice. And by the way, if you have any feedback you want to share, then it's very helpful. Please write it in the comments below. And if you don't have a YouTube account, you will find other ways to contact me, I'm sure. So now we start with an introduction to concepts, and I use this book here. This is Elements of Programming from Alex Stepanov, and you see it's a quite thin book, but so it's only about 200 pages, but it's so dense. So this is definitely not a beginner book, but it contains a perfect definition of concepts. So I'm going to read a few sentences from chapter 1, and I'm going to show some code on the side to explain or to show an example of what that means. He says in concepts, here it's written, A procedure using a type depends on syntactic, semantic, and complexity properties of the computational basis of the type. So on the right-hand side here, I have shown some code. It's a procedure, and Alex Stepanov says that what the code does depends on the arguments of the function, depends on has syntactic, semantic, and complexity properties. So from the syntax perspective, I read, syntactically, it depends on the presence of certain literals and procedures with particular names and signatures. So in the example here, all the procedures that are called by these procedures are actually operators. So, and therefore, whether the code is actually correct depends on whether those operators are correct. So for example, that inequality check here is something that needs to be evaluated as a bool. Putting a star in front of out needs to evaluate to an L value because we use it here on the left-hand side of an assignment. And putting a star in front of it needs to or can be evaluated as an R value because we use it on the right-hand side of the assignment. And putting plus plus in front of it and in front of out needs to be a valid expression. Only if those all expressions are valid, then the whole procedure is valid. I read on. We have semantic requirements. Yeah. Its semantics depend on properties of those procedures. So what our procedure does depends on what those expressions do. So the program only terminates if this not equals end evaluates to false at some point. And we can say that the whole procedure does to a range of elements what the expression, what this assignment expression does to a single element. So if that performs a copy, then our whole procedure performs a copy of a range of elements. And putting plus plus in front of it and out needs to perform an increment. And then we have its complexity depends on the time and space complexity of those procedures. So we can say we have a loop here, we can say that our procedure has linear complexity as long as all the expressions it uses internally have constant complexity. Of course, if you have a procedure where you have when you call another procedure inside a loop, then the complexity of your algorithm will be different depending on the complexity that you use internally. But now it gets interesting. It's about replacing types. He says, a program remains correct if a type is replaced by a different type with the same properties. So if I replace the pointer to int that we have here, the first two I replace with a pointer to float, and the last one is replaced with a pointer to double. Now, of course, this function does something else. It no longer copies a range of integers to another range of integers, but it's now copying a range of floats into a range of doubles. But since the properties are valid, so the pointer to float has the same properties that we depended on when we used the pointer to int, this is still a valid program. And he says, the utility of a software component, such as a library procedure or a data structure, is increased by designing it not in terms of concrete types, but in terms of requirements on types expressed as syntactic and semantic properties. So instead of using a pointer to int or a pointer to float, we turn that function into a function template, and we add requirements on the template arguments. So in this example here, I'm using the syntax from the book. This is not the same syntax that also eventually made it into C++11, C++20. where the requires keyword is now valid understood. In the book, in the example code, he just used this syntax under the assumption that it is valid, and to actually make this compile, requires, which is defined as empty. Anyway, so we have this this copy function now, and this is very similar to the one that we find in the C++ standard library. Only the return type is different, but we don't use the return type in the example. So what he says here, the utility of a software is increased by depending on requirements rather than on concrete types, is shown in the example here. The the C standard library contains a function called memcopy, and as the name suggests, it can only be used to copy memory. The copy function that we just have seen the implementation of can also be used to copy memory. Only the order of arguments is different, right? In the C standard library, the destination is first, and then the second argument is the source, and then the third argument is the number of bytes we want to copy. In the function, in the copy function that we used, also the copy function in the C++ standard library takes the source first, and then the end of the source, and the third argument is the destination. And to show how this is even more useful than, so this function cannot only be used to copy bytes or copy integers or copy floats into a range of doubles, but what it can also do is, for example, copy from standard input directly into a vector. So the input is actually parsing numbers from the standard input, and the output is appending to the vector. And if the vector's capacity is not large enough, this will perform a reallocation. And all this is done, or all this can be done with the copy function if it is implemented in terms of requirements rather than on concrete types. Okay, and then he says, we call a collection of requirements a concept. So this is the definition of a concept. So okay, so if you go back to the here, the concepts are input iterator and output iterator for this copy function. Or in more detail, you can even split the concept. You can say that the input needs to be an iterator plus an input. So you can say those are two different concepts. But more generally, also in the C++ standard library, we have a concept of an input iterator and an output iterator. And then this very metaphorical sentence here. In order to describe, sorry, wrong line, types represent species, concepts represent genera. Very metaphorical. Okay, I want to skip a few sentences and explain more terminology of concepts. In concepts, we have something that we call refinement and modeling. And so, where was it? We say that a concept is modeled by specific types if that the types model the concept if the requirements are satisfied for those types. So this is where we say modeled or modeled by. And a concept C dash refines a concept C whenever C dash is satisfied for a set of types. If whenever C dash is satisfied for a set of types, C is also satisfied for those types. And we say that C weakens C dash if C dash refines C. So this is how refinement works. If you add additional requirements to a concept, that is called a refinement. And if you take away requirements from a concept, that is called weakening. Okay, but now we want to see examples how this is actually used in the C++ 20 ranges library. So we open C++ reference and we go to the ranges library, and you see here that we have range concepts. And the most simplest range concept is a concept called range. So look at this one. We see it has syntactic requirements. That means a range is anything that has a begin and an end. So this ranges colon begin needs to be a valid expression. And what ranges begin does, it invokes the begin function of the range, which can be either a member function or a non-member function. So this is an entry point for the begin function of a range, independent on whether it's actually implemented as a member or non-member function. So it also has semantic requirements. It says that begin and the end function are amortized constant time complexity. But this is not really something that the compiler can check. The compiler can only check the semantic requirements that the function actually exists. Okay, so the range concept is mostly about syntactic requirements. And we go back and we want to see another example here. We have the view concept, which is a refinement of a range. So it has some additional requirements, and I want to read this here. The view concept specifies the requirements of a range type that has suitable semantic properties for use in constructing range adapter pipelines. So what does that mean? What are the suitable semantic properties to make it usable in a view, in a range adapter pipeline? We don't have to go into very much detail what those requirements are. I can only say so much. The semantic properties go far beyond of what a compiler can check. And so we see in the definition, the concept view is just range, and then it adds enable view, basically. So it is the responsibility of the programmer to say to how to say to say that or to decide that the type fulfills those requirements. So the programmer enables the type as a view, and then what the compiler only checks, was this enabled by the programmer? Okay, because it goes far beyond what the compiler can check at compile time. The compiler doesn't know the complexity of an algorithm if it just sees the function definition. Okay, and so that was what I want to show for the concepts. And you see that the ranges library provides other refinements like the borrowed range and the sized range and input range and output range. All those are refinements of the range concepts, and most of those do not really add requirements on the range itself, only on the iterators that are returned from the begin and end functions. But there's something else that I want to show you in the ranges library. It's this view interface here. And this is particularly interesting because it is a name that ends with interface. And yet, for the people coming from Java or C#, this is not a polymorphic type. So this is not an abstract base class with virtual functions that you override. This function, this class does not have any virtual functions. Also, no private virtual function. It does not rely on polymorphic behavior at all. What it does instead, it can be used to extend the interface of your type. We see here this example code. We have a custom class view, and we just implement a begin function and an end function. And we inherit from a view interface, and curiously recurring template pattern is used here, where the type itself is used as a template argument of the base class. And what you inherit from what you inherit from this interface, the functions that are added to the interface of your type, are those member functions here. You get an empty and then cBegin and cEnd and operator bool and data and size and front and back and the subscript operator. So you don't have to implement those functions yourself. All you need to do is inherit from the interface, and then you get those functions for free. What you still have to do, however, is implement the iterator that is returned from the begin and end functions. So this is still something you have to do. But there is a C++ proposal to add something to the standard library. It's called an iterator interface. I want to show that here. And I just read from the motivation here. The story, writing STL iterators is very useful. And the story for everyday users writing STL iterators is not great. Yeah, that's true. We will see maybe at some point when we implement a class for the chain, I will make use of this and show how custom iterators need to be implemented. But we're not there yet. And for what we need now, I want to show another standard proposal, also something that is not yet used. It's not yet available in the standard library, but yeah, I want to show. So this is a class AnyView. This is a standard proposal that is recently added. So it's not in C++ 26, but it might be in C++ 29. From the motivation or the abstract, we can read, this paper proposes a new type-erased view. Std ranges any view. That type-erased view allows customizing the traversal category of the view, its value type, and a few other properties. And you see in the example code here, we have a function, getWidgets. It returns an any view of a widget, and in the function implementation, we have a pipeline with this pipe operator that we have also seen in the Bitcoin kernel implementation that I've shown in a few videos back, and where we did not really know what the type should be that is returned from the function, because we do not want to leak the implementation. The AnyView seems to abstract that implementation. So this is exactly what we need for now. We see there is implementation experience. I have a look. AnyView has been implemented in range v3. They have their own implementation, and there's also an implementation in the Beeman project. So let's try this. I go to the Beeman project, and I scroll down for how to use this. Where is it? Use Beeman AnyView directly from CMake. Let's try this. So we copy this here, and we go in our CMake.list.txt file, and we add it here directly below the other fetch content thing. Copy it in. We already include fetch content. We don't have to do that again. So we can remove this line. And we change the formatting slightly to match our own formatting. And we see that this exclude from all is actually quite useful. We also want to add it to Bitcoin, so we don't have to build things that we do not really depend on. And then we add Beeman AnyView to the dependencies. Here we have target link libraries. We put this one here on a separate line, and we add a public dependency of the AnyView. It's public because we are going to use it in a header file. So add this as a dependency. And then we go to the source file, the header file, the primitives. And here we need to add the include. The include is beaman any view. So add this include here. And now this output type is now beaman any view any view. Then we pass the template argument, which is the type, which is just the transaction output. And the second template argument will be a combination of options. Those are any view options. And we have to say what the options are that we want to type erase. That will affect the exact concept that will be type erased. We want this because we are, if you go to the implementation, we see we have a vector. A vector has constant is a random access range, and it has a size. And we want to transform that so that resulting range still is a random access range with a size. So our options will be random access, and we OR that together with size. I think it's written like this. So sized. And then the third template argument, we also give the value type, transaction output, because we are transforming. Therefore, the reference type, which the third argument is the reference type. We cannot return a reference if we perform a transformation, but we can return a value. So the reference type, we just use the value itself. Okay, then we try to compile this. Wrong window. Okay, we go to the build directory and we run the build, and we see it's building. What was wrong? What is this? This was not planned. Oh, I forgot to save. Okay. Okay. Run again. Oh, it's building. Okay. Interesting. That is a surprise. What was built? Let's run it. It prints 2. Where does the output come from? What did we have in our implementation in the test? We see we print the output size, and it prints 2. So apparently this transaction has 2 outputs. What else can we do? On the outputs, let's try to access the first element. So we type tx dot outputs. We run first and see where no, it's not called first, it's called front. And according to my IDE, there is no problem, but let's see what the compiler says. We run the build, it's successful, and we run the binary, and it says the output is 2, and then it prints convert. And where does convert come from? Right, in our conversion function, we output convert. So since convert is printed once, we have proven that the conversion function is only executed once. So if the range that we return has 2 elements, but we only access a single element, we only apply the conversion function a single time, which is great. And this is now allowing us to hide the implementation and still give access to a range. Yeah, that is great. This is very helpful. This is what we wanted. And why this is so useful, I will explain in the next video. So thanks for watching. Make sure to subscribe to the channel so that you don't miss the next video. And goodbye. Thanks.